All right. We are going to do like 3 slides, finishing up the fluids, and then get to thermodynamics. So we're just going to be looking right here at these bottom 2 things that we've talked about, actually the bottom one only. So when we have a fluid flowing, if it doesn't have gaps, if it's continuous, then we're going to have something happen when it goes from one diameter to another. If we have it continuous, we're going to have the same amount of water molecules passing any place per second. But if you have a smaller size tube or smaller size pipe, what's going to happen to the speed they're traveling if you have the same number of molecules per second passing? Not slow down, you have to speed up. If it's a smaller opening to get the same number of molecules through per second, they're going to have to be traveling faster. So the speed gets faster when you go from larger to smaller. But of course, we learned from the Bernoulli relation what happens to the pressure when the speed goes faster. It goes down. Pressure drops when the speed goes up. So that means it's going to be faster and lower pressure, slower and, I should put pressure there, and higher pressure.
So why is it the case if like the amount of area that you have now is smaller? I thought that whenever you are compressing something into a smaller space, it would be more pressure.
And that's a reasonable thing to think. If I just have a confined space and compress it, that's what's going to happen. But this is a fluid flowing through. And since it's flowing through, you have a certain continuity, right? Pressure one place affects pressure another place. But if it's speeding up, it's going to lower the pressure where it's speeding up. So if the elevations stay the same, and it's going faster one place, it's going to have a lower pressure. Now, if you go up, what does it do to the pressure if you go up higher? Decreases, right. Because you have the pressure changes with depth, rho GH, as we had on the quiz question yesterday. So here, our first clicker question. And unless I go fast, likely our only question, so make sure you answer. What happens to the internal water pressure in a narrowing pipe of moving water? So that's saying, what happens to the pressure when you go from here to here? Okay, everyone's answered. That is weird. It actually worked without a hitch. I did like 7 things before class in hopes that one of them would work, and maybe I hit it right. If only I knew which one it was. So, 6 people said the pressure is lower, 2 said the pressure is higher. Getting down to the final 2 before we start over. Leslie, what do you say?
Since we're talking about fluid flow, when you're getting from a larger pipe to a lower pipe, then that would make whatever it is, the speed or whatever increase, but then the pressure is going to go down. I guess
Perfect.
It has to do with that rho something formula.
The Bernoulli equation, which we didn't learn the formula here. It's the actual equation for it is pressure 1 plus 1/2 rho V1 squared plus rho GH1 is equal to pressure 2 plus 1/2 rho V2 squared plus rho GH2. The left side and the right side are exactly the same except for the subscript is changed from 1 to 2. That's the actual Bernoulli equation that tells you how the pressure, the speed, and the elevation all relate together. But we don't have to know that equation. We just have to know the idea: faster speed, lower pressure. So this is one application we talked about last class period. Air blows over the top of a house, lowers the pressure on the top. Pressure inside, because you have still air, is higher, and it tries to pop that roof off. Or the airplane wing, you have the air splitting, so you have air going underneath, a shorter distance because it's pretty flat, air going over the top. Well, that was a good job. I was trying to trace. A longer distance. You can also tell from the picture relative speeds by how close the lines are together. When the lines are closer, it's moving faster. And so lower pressure on top, which means if you look at the forces, the force down is equal to the pressure on top times the area, and the force up is equal to the pressure on the bottom times the area. And because it's going slower on the bottom, it has a bigger pressure, and thus it's pushing up more than it's being pushed down. And that's how airplanes fly. It's, I think, a little more scary to know how an airplane flies than it is to just know they fly. Because when you realize, wow, it's just because the different speed of the air on top and bottom, it doesn't seem like it's all that much holding you up there. Okay, that's the end of our fluids talk, and we're going on to talk about thermodynamics. Thermodynamics is talking about temperature and heat and how these things relate. So you can see a lot of topics here, and we'll just have to see how far we get today. So temperature, I've already mentioned what temperature measures. I said that temperature measures, well, I didn't put it on this page. Fundamentally, what did I say temperature measures?
Kinetic energy per molecules.
Yes, average kinetic energy of the molecules. And it'll be coming up on a later slide again. But temperature is measuring average kinetic energy of the molecules. What we generally think is temperature is just measuring how hot something is, hot or cold. Hot means that the molecules are moving rapidly, have a high kinetic energy. And we measure it with the thermometer. I didn't bring out a thermometer because I figure everybody's seen a thermometer. Instead, I brought out something that's more cool. Now, this requires me to make fire, and I am much like caveman. It's a hit and miss thing if I'm actually going to make fire. So far, so good. This can also be used as a temperature gauge. What is this thing? It's not an ice pick, by the way. So I will come to the nearest student. Gabby, what is this? Well, just describe it for the others.
It's like a metal stability thing.
Now I'm going to have her help me because I'm so hoping students will come get extra credits and see what kind of fun it is. Come with me. Now what you're going to do is, without getting your sleeve on fire, just want to make sure we're cautious. Stand on this side so they can see, and hold that in the flame.
Do I take it out or leave it?
Ah, keep it in there.
What?
Is that cool or what? Now, since you're up here helping me, tell them what's happening. That way it'll be on the recording.
Oh, it bends inward.
Okay,
Like a swirl.
it curled when she made it hot. What's happening now that it's cooling?
Straightening out.
So you can clearly see that that would also work as a thermometer, right? And if you have like a garden thermometer that you've seen, it just has like this big spiral, looks like a spring. This is what it is. Now, what is this? It's two different types of metal. If you look carefully, this side looks more blue-gray, and this side looks more orange-gray. They're different kinds of metal, and the metals will expand when they're heated. But they expand by different amounts when they're heated because they're different types of metal. So the blue-gray side doesn't expand as much as the yellow-gray side, and so that makes it curl up, which is totally cool, right? I mean, it's physics, so of course it's cool. It's kind of redundant. So that can be used as a thermometer. The garden thermometers that you often have, it's a really long bimetallic strip, two types of metal, and so as the temperature changes, one side's getting longer compared to the other, and it curls a little more, and then indicator moves, and it's calibrated to show you the temperature. The kind of thermometer that you're used to seeing that has the little fluid in there, the fluid used to be mercury. These days we consider mercury dangerous. And so now they often are just using alcohol. That alcohol is also going to expand when it gets hotter. And so it expands in the tube, and because it's taking up more space, you see the level moving. Excuse me. So that's what a thermometer does. And notice it says it's a per particle property. That's referring to measuring the average kinetic energy. Temperatures have a lower limit of an absolute zero is what we call it. There's a lower limit on temperature because kinetic energy has a minimum value. What's the lowest possible kinetic energy you can have? 0. And so temperature has an absolute minimum that occurs when you get to that 0 kinetic energy. Now, it turns out you can't actually reach 0 kinetic energy, quantum physics says, but as you approach 0 kinetic energy, you approach that absolute 0. And there is no upper limit on temperature because you can always increase the energy of something. So temperature has a minimum but no maximum. Here is the one that's talking about the kinetic energy. Temperature is proportional to the average translational. What's translational kinetic energy? That's moving as opposed to spinning. So you have rotational and translational kinetic energy. And you have, if it's a solid, you say, well, those molecules aren't moving. They're fixed in place in a solid. But they're actually vibrating about a fixed spot. And so there is motion even in a solid, and your temperature is telling you about that. The relationship between temperature and average kinetic energy differs by material, but it's proportional. A couple things about thermometers. Number one, when you pop the thermometer under your tongue, it doesn't immediately show your body temperature. Why not? Why does it take some time to show your body temperature?
Your thermometer is already the temperature before that, so it has to be able to adjust to equilibrium. Is that what it is?
Your thermometer is not at your body temperature, and it has to warm up, usually, to your body temperature, and so it takes time for it to warm up. You're actually measuring the temperature of the thermometer. They say a thermometer measures its own temperature. And so you have to get that thermometer to warm up to your temperature for it to read your temperature. So it takes some time. If you use an infrared thermometer, these days they'll do things like, put a little thing and just point it in your ear, basically. And in that case, it's looking at the actual radiation your body gives off. You give off radiation like light, except for not in the spectrum we can see, and it's measuring that to determine your temperature, which is kind of cool. Now, some temperature scales. The oldest of the temperature scales we use is the Fahrenheit scale. Gabriel Fahrenheit created a temperature scale, and we usually write that temperature scale as having 32 degrees Fahrenheit as the temperature of freezing water, and 212 degrees Fahrenheit as the temperature of boiling water. Now, when he devised this scale, it's not 100% clear. I have read different historical accounts. But by general consensus, he used something like the temperature of seawater when you had ice and seawater mixed near his home as the 0 temperature for his calibration. And he used body temperature for the 100 degree calibration. So he calibrated between a 0 and a 100 steps. Biggest problem with his calibration is it depends on the composition of the water, what temperature it's going to freeze at. And so you have more salt, it's going to freeze at a lower and lower temperature. So the calibration there for the 0 is kind of odd. And then body temperature If you get sick, your body temperature changes. Your body temperature is different when you get up than when you go to bed. So that's not a very good calibration point either. Now, just a couple years, I think it was about a dozen years later, Anders Celsius came up with his temperature scale. And like Fahrenheit, Celsius used 100 degrees between his two calibration points. But his calibration points were the freezing temperature of pure water, not ocean water, pure water, and the boiling temperature of pure water. And so you see 100 degrees, that's the two calibration points for Celsius' scale. For Fahrenheit, it was that range. Which of these is a better system? Well, you probably know. We use in science exclusively Celsius scale. But here's a couple funny things, historical things that you don't need to know. So please don't put these on your potential test questions. So, number one, Celsius, when he originally made his scale, he made the temperature of freezing pure water 100 degrees Celsius and boiling pure water 0 degrees Celsius. That's upside down, right? And he died, and about a year later, people said, well, this is ridiculous. They flipped it over. So the scale we now know as Celsius is actually flipped from what he used. But there's another thing. Have you guys ever heard the term centigrade? Okay, good for you. When I was a kid, we talked about centigrade and Celsius. Centigrade, centi means 100, like there's 100 cents in a dollar, 100 centimeters in a meter. Centigrade means there's 100 units, in this case, the calibration. And so we called the Celsius scale the centigrade scale when I was a child. And it caused me great confusion, because we changed over to the metric system when I was a child. We changed back because people said it was confusing. I think I mentioned that. And it also occurred about the same time that we changed to and from the metric system, that the Celsius scale was taken off of the centigrade. It's no longer a centigrade scale. They changed the calibration point. Well, one of them. Now, instead of calibrating at 0 degrees Celsius, they calibrate at what's called the triple point of water. The triple point of water, and this is something you can use. The triple point of water is the temperature and pressure where pure water can exist in all three of the common states. Pure water will be liquid, solid, and gas, all at the same temperature and pressure. There's only one temperature and pressure combination where that's possible. That makes it a really good calibration point because anywhere in the world, if you get pure water, you put it in a vacuum chamber, you get it down to the point where all three coexist, and that's 0.01 Celsius. So it's very reproducible. So now the Celsius scale, instead of being a centigrade, is a 99.99 degree in its calibration. So close to centigrade, right? But not quite. The Fahrenheit scale is now calibrated based on the Celsius scale. So the Fahrenheit scale is no longer calibrated by anything except for how it matches up with Celsius. And so the connecting points for the calibration of Fahrenheit are those two. That 32 degrees Fahrenheit is the same as 0 degrees Celsius, and 212 degrees Fahrenheit is the same as 100 degrees Celsius. That's how it's calibrated. Now, if you look at those numbers, you have a span of 100 degrees here and a span of 180 degrees here. So a change in temperature of 180 degrees Fahrenheit is exactly the same as a change in temperature of 100 degrees Celsius. Now, if you take those and divide them, 180 divided by 100 is, of course, the same as 18 divided by 10. Those are both divisible by 2, so that's 9 over 5. So 180 degrees Fahrenheit. Actually, when you're going to do a change in temperature, you put Fahrenheit degrees. that also you don't need to know. So don't put that. So 180 per 100 is 9/5.
So is it wrong to put degrees Celsius instead of Celsius degrees?
If you're talking about a temperature, you should put degrees Celsius. If you're talking about changing temperature, you should put Celsius degrees. Yeah, but something trivial, because no one actually follows the rule.
Yeah.
So the ratio there is 9/5. So which is a bigger degree? Well, you have 180 degrees in the span of 100. That means the one that has 180 is a smaller degree. So a change in 1 degree or 1 Fahrenheit degree, right, doing it correctly, is roughly the same as a change of a half a Celsius degree. Thus, when you're looking at temperatures, we often just look at the temperature in Fahrenheit as an integer. You know, it was 8 degrees Fahrenheit this morning when I woke up. Whereas with Celsius, they usually use 1 decimal place because the Celsius is a bigger amount of temperature change for 1 degree. Because it's about twice as much temperature change for 1 degree for the Celsius scale. Now, to convert between the two, you just take those numbers and you take this. 0 degrees Celsius is equal to 32 degrees Fahrenheit. So that means the temperature in Fahrenheit is going to be the temperature in Celsius times that 9/5 that comes from 180 degrees in the span of 100 degrees, and then plus the 32 that comes from this relationship. So that's our conversion factor for converting between Fahrenheit and Celsius. And since Celsius is the one that's carefully calibrated, that's what everybody does. The Fahrenheit is simply calculated that way from the Celsius. Now there's another temperature scale here, the Kelvin scale. Lord Kelvin, and you can see, looking at the lifetimes of Celsius and Fahrenheit, they lived roughly the same time. They were pretty much contemporaries. I'm sure Fahrenheit was 15 years older. But Lord Kelvin was born after both of them had died. Lord Kelvin said we should make a temperature scale that has 0 is the minimum temperature possible. So by this time, there was good understanding of, well, absolute 0 is minus 273.15 Celsius. It says minus 273 here. And so the Kelvin scale is simply the Celsius scale shifted by 273.15. So that means 0 Celsius is 273.15 kelvins. Right, you just take the Kelvin temperature, add 273.15, and you have the Celsius. Or if you want to go the other direction, you take the Celsius and no, I said it wrong. Yeah, I said it wrong. So if you want to do it the right way, you take the Kelvin temperature, add 273, and you get Celsius. Or you take, no, I said the same thing again. Take the Celsius temperature, add 273, and you get Kelvin. Take the Kelvin temperature, subtract 273, and you get Celsius. So temperature Kelvin is equal to temperature Celsius plus 273.15. So temperature Kelvin is based on temperature Celsius, and temperature Fahrenheit is based on temperature Celsius. And you can invert this equation to solve it for temperature Celsius as a function of temperature Kelvin. Instead of 5/9, it's 9/5. Temperature Fahrenheit minus that 32, because you got to take care of the offset.
Oh, when you're switching to Fahrenheit?
When I'm going from Fahrenheit to Celsius, I use the black equation. From Celsius to Fahrenheit, I use the blue equation.
Do you want us to know how to convert back and forth?
Well, you'll have all equations on the exams. That reminds me, a number of people have been putting what's the equation for as their potential test question. Since the exams will have equation sheets that give you all the equations, Those aren't very good questions. I've only been taking off one because I want people to, not lose a lot of points by making a mistake. But I'm going to switch that to taking off 3. So don't put in what's the equation, because those are not usable on the test because you already have all the equations.
Like you'll give us an equation like that to know how to convert with
Yes.
Kelvin Celsius too?
Yes, that's right. Because in physics, we're really not concerned about you memorizing stuff. We want you to understand concepts. But we're not worried about you memorizing stuff. It's understanding the concepts, understanding how they fit together that we're looking for. Okay, this is just a picture to illustrate the range of temperatures we have. So you see down here at the bottom, the temperature where helium boils is way down here. Oxygen boils at minus 200. You get up to, ammonia boils at still below 0 Celsius. Get up to water boiling temps. The surface of the sun, 6,000 kelvins. Notice we dropped off the Celsius. The difference in Celsius and Kelvin is that 273. By the time you get to 6,000, it doesn't matter too much. By the time you get to the temperature in the core of the sun, there is no difference between Celsius and Kelvin. 20 million, what's 273 among 20 million? If I had $20 million, I probably could afford to lose 273. Unfortunately, that's not the case. And the temperature for a hydrogen bomb, 100 million kelvins. That's some hot action there. It's not the hottest that's theoretically possible. What's the maximum theoretically? There is none. It goes on forever. Of course, getting up there is going to be pretty hard. So talking about absolute zero, and I'm going to jump right to the third law of thermodynamics. We have 4 laws of thermodynamics. The 0th, the 1st, the 2nd, and the 3rd. How's that work for you? The 0th. No, they weren't computer programmers who simply started counting at 0. The 0th law is one they thought of after they'd come up with the other ones. They said it's so fundamental, let's put it first. The 3rd law of thermodynamics, and I have a slide on this coming up, says temperature cannot reach 0 kelvins. It cannot reach absolute 0. And there's some easy explanations I'll get to later, but that's the 3rd law. You can't reach absolute 0. It's a theoretical limit. And you're not going to ever reach that limit. You can get very close. Scientists have done experiments where they get down to microkelvins. Micro is, 1/millionth. So they're down in the 1/millionths of kelvins, very close to absolute 0, but you can't reach absolute 0. If you were at absolute 0, you would have lost all available kinetic energy. Notice that's all available kinetic energy because quantum mechanics says you've got some issues. You can't lose it all in most cases. Now, heat. How many people in the last month have said, turn up the heat? Most of us, even me, perennially hot. Heat is something that we often don't understand very well. Heat is not the same thing as temperature. Hot and heat aren't describing the same thing. Heat is actually talking about energy movement. It's not energy, it's energy movement. So nothing can possess heat. You can be hot, but you don't possess heat. You can give off heat, that is, energy can leave you, but you didn't have that heat, you had energy. And when energy left you, then it's called heat. So heat is a transfer of energy. And one statement of the 2nd law of thermodynamics, one statement is that one there. Heat naturally flows from hotter materials to colder materials. So let us say that I had this burner on and it was at, 1,000 Kelvin or 1,000 degrees Celsius. If it's 1,000 degrees Celsius, what's my fingertip temperature at? What's body temperature? Okay, 98.6 is our standard for body temperature. In Celsius, we'll just go with 37. So that's like 1,000 Celsius, and my finger's at 37 Celsius. When I touch there, the second law of thermodynamics says heat is spontaneously going to move from the one at higher temperature, from that thing, into me, the one at lower temperature. I'm gaining energy. That's great, right? I'm getting more energy. It's not an energy I can use. It's only an energy that can cook me. I don't really like gaining energy that way. I much prefer to get it in the form of cheesecake. Except for now that I'm vegan, cheesecake is off the menu. So is the 5-cheese pizza Da Vinci's. If you're not vegan yet, you should go eat that 5-cheese pizza before somebody says you got to be vegan. It's really, really probably very fattening. So the second law, one statement is that heat naturally flows from hot things to cold things. So if you put things in thermal contact, that means you make it so heat can flow. One way of putting them in thermal contact is making them physically touch. Then heat will flow from the hotter one to the colder one until you reach equilibrium. Equilibrium means, in this case, the heat stops flowing. Well, if heat always flows from the hotter one to the colder one, if the heat stops flowing, what does it tell you about the temperatures? They're equal. That actually brings us to the 0th law of thermodynamics. It seems so obvious, no one ever thought you would ever have to say this. Here's the 0th law of thermodynamics. Now I'm going to say lots of words and then I'm going to write one succinct equation for it. If object A is in thermal equilibrium with object B, bunch of words there. But if we analyze it, what does thermal equilibrium mean? I just said. It means that they have to be the same temperature. It means you put them together and no heat flows, which means they're the same temperature. So that if object A is in thermal equilibrium with object B, can be written equation-wise as if temperature A equals temperature B, and if object B is in thermal equilibrium with object C, which can be written succinctly as what? Yep. Then, what do you think is going to be true? That seems really, really stinking obvious, doesn't it? But it turned out as they understood more and more about what temperature was, it suddenly became, ooh, that didn't have to be. Because after all, it's measuring the average kinetic energy, but it's not equal to the average kinetic energy. And so it didn't have to be that way. And so they said, wow, that's an important statement. It's something very fundamental. And so they slipped it under and said, we're going to call this one the 0th law of thermodynamics. So we've actually talked about 3 of the laws of thermodynamics already. 0th law, if object A is in thermal equilibrium with object B, and object B is in thermal equilibrium with object C, then object A is in thermal equilibrium with object C. Or if temperature A equals temperature B, and temperature B equals temperature C, then temperature A equals temperature C. That is it. That's the 0th law. So we've seen that one. We've seen the second law with one of the statements. There are multiple statements of the second law, and this is one of them. That heat naturally flows from higher temperature to lower temperature. Naturally flows from a hotter object to a colder object. And then we've seen the third law that says nothing can ever reach absolute 0. Can come very, very close, but can't reach it. Only leaves one more law. Unfortunately, it's not on the next slide. We'll get to it today. We want to stick, actually, I'll put the first law because the first law is the most important one. First law, we've mentioned it in previous lectures. Energy cannot be created or destroyed. You can convert it. So we can have something like a gasoline engine that will convert chemical potential energy into thermal energy, and then that thermal energy into mechanical energy. We can do these transfers of energy, but we're not creating energy. When you burn gasoline in your car, you're not creating energy. You're just transforming it. So it can't be created or destroyed. And the reason that equation, or that's not yes, we usually write an equation for this that says delta U is equal to Q minus W, but you have to know what those things are before the equation makes any sense. So that's why it hasn't shown up yet. So how do we measure heat? It's a transfer of energy. So the standard would be to use a joule, because joules are the units for energy. But the development of thermodynamics took a funny path. It was thought that you had a caloric and a frigidic, two fluids that flowed. And the caloric would bring warmth. It would bring heat. The frigidic would bring cool. And so if something was getting hotter, well, it'd have to have more caloric flowing in than it had frigidic. But then we had Joule who said, well, observed that, I think it was Joule observed that in boring out a cannon, that the cannon got really hot when he was boring, and so he had to cool it. And he said, I think that the work I'm doing to bore it out is what's making it hot. It's not some mythical fluid. And so he did an experiment where he dropped a weight and had that weight turn a beater in water. And he measured the temperature change in water to measure how much the water warmed up. And he found out, yes, indeed, the amount that the water warmed up was proportional to how much work he did on the fluid. And so then it was understood, so the heat is just energy flowing. It's not some mystical fluid. But they already had this caloric and frigidic thing going. And so they had the unit of the calorie to measure how much heat was flowing in the caloric. And so what Joule did was he found a calibration that 1 calorie was 4.19 joules of energy. And so now we have 2 units for heat. Which one is the standard one? You could get this wrong. It's not obvious. It's actually the joule. The joule is the standard unit. And so if you go to many, many countries where they are on the metric system, you get your can of Coke, and it will say this many kilojoules instead of this many calories. Because it's telling you how much energy you're going to take in by drinking the can of Coke. That's the way we like to take in, well, not Coke, because Coke's not good for you, but that's the way we like to take in our energy is by eating less.
So then here in the U.S., are we the only ones that use calories?
I don't know who else may use calories, but we are, I'm pretty certain, in the minority, yeah. We just use different units than the rest of the world. We're special. We're like Kansas City Chiefs fans. We get to ride in the short bus. I don't know if you've been to a football game, but that's the way they get there, the short bus. It's like their preferred, you guys know what I'm talking about, right? Their preferred form of tailgate parties is to have a little short bus. It cracks us up as non-Kansas City fans. So when you're counting your calories, you're counting the energy that's coming from the food. Now here's something you don't know. It's coming up in a slide, but I just have to measure it now. When you count your dietary calories, you're actually counting kilocalories. What does the prefix kilo mean? Okay, so 1 dietary calorie written with a capital C is equal to 1 kilocalorie. or 1,000 calories with a lowercase c. How's that for confusing? A dietary calorie is 1,000 calories. It's easier when it's written down because at least you can see the capital C. When you say it out loud, it sounds more difficult. So when you're looking at how many calories that food has, this beautiful chocolate muffin has 800 calories. That's 800 kilocalories, with 1 calorie being 4.19 joules. So it's 800 times 4,190 joules. That's a huge amount of energy. It's enough energy to keep you going for pretty much the entire day. Now, you will lose weight if you only eat one. Eat two to be safe. Then you won't lose weight even. Or maybe just don't eat those wonderful things. That's the way my wife thinks. You just don't eat the bad things. It's smart, right? Just got to put in a plug there for that's smarter than the way I think. Tell her I said that because she'll be shocked. Okay. The measurement for the calorie is based on how much energy it takes to raise the temperature of water. So 1 calorie is equal to the heat required to raise 1 gram of water by 1 degree Celsius. Hey, at least the calorie is based on metric units. It's not our standard unit for heat, but it's based on metric units. Of course, here in America, we've got to muddle the waters. If you go shopping for like a furnace or an air conditioner, they're going to measure the heating or cooling in the BTU. Anyone heard of a BTU? It stands for British Thermal Unit. Of course, we use the British Thermal Unit here because why would we use something that the rest of the world might consider reasonable? The British Thermal Unit is the amount of heat necessary to raise 1 pound of water by, is it 1 pound? I think it's 1 pound of water by 1 degree Fahrenheit, something like that. Okay, so I clearly don't use that unit, or I would know exactly the definition instead of saying I think, but I'm pretty sure it's not a slug of water. I think it's a pound. So, symbol for heat. Have you figured out what the symbol for heat is? I wrote it down once. The symbol for heat is Q. But don't worry, in the next chapter, Q is going to be charged. Life gets confusing. Question, Danny?
I'm just confused. Why it's Q?
I don't have an answer.
That's why I was
I don't know why it's Q. So Q is heat. Maybe for quantity. What do you think? I don't think that's valid, but you say what?
I said no, just for the sake of confusion, let's just say quantity.
Okay. So because the calories defines the amount of heat necessary to raise 1 gram of water by 1 degree Celsius, it's pretty clear if I want to raise 3 grams of water 1 degree Celsius, I'd have to have 1 calorie per each gram. And so the example here is if I have water, if I want to raise the temperature from, let's say, room temperature, 20 degrees Celsius, to boiling temperature, 100 degrees Celsius, the amount of heat necessary is proportional to how much water. If I have double the water, I'm going to have twice the heat to get that temperature change. Because the heat is going to raise the temperature in a linear fashion. Yeah, it's a good approximation. So here's the discussion about the calorie, the dietary calorie. And so the kilocalorie with a capital C is using a kilogram of water. Yeah, it's kind of silly, but it's true. So this is a practical example. To the scientists, when you eat a peanut, okay, a peanut that has 10 calories. 10 calories, I'm like, pfft. Right? You look at dietary labels, and it goes like if you go to look at dietary information, if you drink like one serving of Diet Coke, it has 0 calories. And if you drink 2 servings of Diet Coke, how many calories does it have? I'm pretty sure it's 10 calories. And you're like, wait, how'd that go from 0 to 10 just by you drinking the second serving? Because they just round to the nearest 10, because they're like, what's 10 between friends? But that 10 calories that you get in one peanut is 41,900 joules. That's a lot of energy. You know, I mean, let's say that I am lifting weight and my arms are about 1 meter long. So let's say I want to lift a weight a height of 1 meter. How big is the force of gravity going to have to be to equal 4,100 or 41,900 joules of work? What's the equation? Okay, you don't have to have equations memorized, so I'll tell you. The equation for work is force times the distance parallel. And if that's going to be 41,900 joules, then the force is equal to that 41,900 joules divided by the 1 meter that I raise it. That's 41,000. That's not a 1. 41,900 newtons. Now, newtons probably doesn't mean much to you, right? Reasonable to say? Okay, so let's put that in perspective. 1 kilogram times 9.8 meters per second squared is equal to, of course, 10 newtons. So if I take this and divide it by roughly 10, that would give me the mass in newtons. So the mass is about 4,190 kilograms, or the mass in kilograms. I said mass in newtons. Mass in kilograms. 4,190 kilograms. And 1 kilogram's weight is not only 10 newtons, it's also 2.2 pounds. So if I take that and multiply it by 2.2, that's going to be somewhere around 9,000 pounds. Eating 1 peanut gives me enough energy to raise 9,000 pounds a meter. Now, I don't have the strength to do that. It should give me enough energy to do a whole lot of reps at a weight I can do. So we don't think about just how much energy is packed into our foods. Okay, now we get to the first law of thermodynamics. The first law of thermodynamics, as I said, energy cannot be created or destroyed. And so we apply that to a single system, and we say that heat added will increase the internal energy. And then we can also have work done by the system. So we have 3 symbols here. U is equal to the internal energy. Once again, don't know why. So U is talking about all of the energy contained in my system. My system might be a cup of water. It might be a block of iron. It's whatever I define it to be. U is the internal energy. Q is equal to heat added. So if you have heat added, remember Q is a change. You're moving energy with Q. And W is work done by the system. And so the relationship we make between these is the change in the internal energy is equal to the energy you add via heat minus the energy you take out via work. Now, it seems odd to have the heat is added and the work is taken out. And so some textbooks actually change the sign to say, we're just going to redefine the work, energy added by work, and the energy added by heat. And they'll change the sign. But this is the standard. The change in internal energy is the energy added via heat minus the work energy out via work. Okay, have a happy Sabbath, and I'll see you again on Monday.